our next speaker is Professor Daniel Zen. Professor Daniel Zen is working in the Department of Civil and Environmental Engineering at Hong Kong Polytechnic University. His research emphasizes a strong link to social needs and real-life environmental challenges. He aims to advance the fundamental knowledge and develop low-carbon engineering solutions to actualize sustainable development goals. He performs interdisciplinary and translational research in natural and engineered systems. Professor Zen serves as AE for a couple of top journals. Today, his topic is sustainable urban drainage system with Biochar Amendment. So, Professor Zen, please.
Thank you, Professor Du, for a very kind introduction. And I'm very glad today to talk after Professor House. After Professor House brilliant talk about the sustainable remediation and the concerns about sustainable developments. So that set a perfect grounds for the talk. Basically, I'll try to focus more on the sustainable drainage, urban drainage system. So regarding the stormwater treatment, the surface runoff, and potential application of biochar for the enhancement. And to start with, I also would like to thank Professor Xi and Professor Tang from Nanjing University and Jing Tao from Nanjing University for their very kind introduction. And I'm glad to be one of the speakers to share what we are doing in Hong Kong with all of you who are attending the ISEG, which is a long-standing and a famous society. And I also attended yesterday's section, and Professor Du's talk is also very comprehensive and brilliant and informative, and I also obtain a lot and learn a lot of useful information from his talk as well, and other speakers too. So I'm sure the audience of this workshop or conference will be benefit a lot with many distinguished scientists and researchers around the world. So I'm really honored to be one of them. So to start with, basically the motivation for these studies, I just want to make sure, because yesterday we have some problem with the slides movement. So I'm moving to the second slide. So
yes, please.
You can see it, right?
Yeah, okay, perfect.
Okay, good. Thank you. So today I would like to share 3 case studies in Hong Kong that I'm involved as an investigator in collaboration with the government. So 2 are the field scale projects, 1 are the pilot scale projects. So these are all beyond the lab scale. So some of the findings are based on understanding are based on our previous lab scale studies. But the major motivation as a city is we would like to deal with the climate change as well. And in the blueprint climate action plan 2030 plus, which is like a 10-year blueprint of the government, and the infrastructure is important. Infrastructure development is important regarding the drainage and flood management, because we are in the subtropical region, which we have a high rainfall. We have like annual rainfall like 2,400 millimeter on average every year, and which are largely intensive in the summer times around these times. So so there's a very intensive rainfall, and flooding is a concern. So we would like to deal with the surface runoff, the stormwater, and then the measures that we have in Hong Kong. So you can see these I'll take and question marks and text are actually what I add on. It's not from the original documents. The original documents, so that all these features are important infrastructures, and we have previous studies with the text, with other scientists or professors in Hong Kong. While for the question marks that we haven't had enough study, we haven't had a field scale, pilot scale studies in Hong Kong before. So that's what we are contributing from PolyU to contribute to the concept of sponge city. And in Hong Kong, we call it more like a blue-green infrastructure. So to integrate the blue infrastructure and the green infrastructure together, so that the citizens can appreciate a better environment. So what we integrate them in, for example, we integrate the concept blue green infrastructure or sponge city in the new development areas, like the areas in Kwun Tong, which was a former quarry site for construction materials. So after the quarry has been completed, it has been turned into a residential area. So there's an integration of blue green infrastructures like the retention flood lake, like a Bowswell and Bow retention rain garden, or bioretention fuel cell, they are all integrated in the new development areas. And also for the Northwest New Territories is even bigger city development plan, the Hongshui-Kiu development areas, which I'm serving as an expert reviewer and advisor for the development as well. The government is also working on the blue-green infrastructure in a larger scale as well. So with these kind of infrastructures, we are dealing with the try to deal with it with the surface runoff at source and try to integrate some passive measures, so there will be less environmental burden and less cost intensive. So compared to the conventional active treatment like the wastewater treatment plants. So we would like to attenuate the runoff volume to deal with the flood risk. And also at the same time, we would like to see whether we can improve the water quality. So the water quality is also associated with the sustainable development goals, like Professor House explained earlier in the previous talk, which is one of the SDG to enhance the water quality and the living environment for the biodiversity as well. So our surface water can be partially treated before they go to the receiving water bodies.
升力可能是就是上升然后下降。对。
Okay, so maybe let me continue anyway.
Yeah, I'm sorry. The audience, could you please mute your microphone? Thank you.
Thank you.
Yeah. Yes, Professor Zen, please.
Yeah. So maybe I move forward quicker. So we have some other design manuals in the UK, in the US, Australia, and Singapore, for example, and we make very much with that. So let's go to the field scale studies that we work with the government. So for this, we're working with the DSD. In the previous one, for the new town development, we are working with CEDD, which is the Civil Engineering Department. And then for the SUDS, we're working with the Drainage Services Department, DSD. So this is in Kwun Tong, which is they're dealing with the river, which is an open water channel for the drainage. And we would like to turn them into a river park. And then for enhancing the water quality in the upstream part, we are going to do with some filter system. And before a filter system, we have some monitoring activities over a year to assess the water quality. And we see that there will be some exceedance in terms of the dry season or sometimes wet season regarding the suspended solid and so on. The red lines represent the discharge limit. So some of the days are actually exceedance in different locations along the river. And then in some of the days, especially with the dry season, you can see that there will be even more exceedance in terms of like E. coli and COD and BOD as well, and they appear together. So the exceedance are associated with the water quality, which are more severe in the dry season compared to the wet season. So as a summary, that we have a certain % of the exceedance in terms of different water quality indicators, like the SS and ammonia is good, oil and grease is good, and COD and BOD sometimes BOD, but COD sometimes, and E. coli and SS. So basically, E. coli associated with SS are the major concerns. BOD and COD are minor concerns, while ammonia and so are good. We don't have problem with that. And mainly the more serious exceedance are happening in the dry season. So we are dealing with the field scale test and the design with the filter system, which we would install the in-stream filters with the different size of the gravel or the rocks and the sand that we chose to evaluate the performance for the field improvement and upstream for the quality. So in the first couple of stages, we work with the wet season, and then eventually the wet season that you can see that with the wet season, a lot of the soil erosion being run off together with the heavy rainfall in the wet season in summer times. So eventually the filters cannot be running too long. So the blue line are the infant quality, while the red line are the effluent quality that we collect with the sensors, inline sensors on real-time inline sensors continuously. That we can see that the filters can effectively work. But the problem, comparing the, where's my cursor? The blue line is infant, red line is effluent, so we can see there is work very well with the different size. But then the problem is the clogging. So eventually that there will be some clogging issues in the wet season. And so we actually focus more on the dry season application. So because we see from the baseline that dry season are more serious with the exceedance, and also dry season may be more appropriate with less amount of the clogging issues without too much flow rate or flooding. So we revise our design, like the engineering design, which you can see we revise our design in terms of in view of the lessons learned from the wet season. So we revise the design, and then we operate another couple 1 or 2 months to this round for 1 month, the next round for another 2 months for the monitoring. And you can see that the blue line, the influent, can be effectively removed until a certain point that we may see clogging, that there are some issues. And the clogging actually associated with the size of the filter, that we can see the smaller size A and D on the side of the filters get clogged earlier, while in the middle the largest and second largest size B and C are performing more consistently, more steadily. So that would be appropriate, from this second round of the test. And then we further proceed with the third round after some maintenance job with the cleaning of the filter materials. And then we run for another 2 months for the third round until clogging appear. And we'll see that in this case, the module C is actually the best compared to before. In the second round, module B is the best, which is a smaller size, while in the third round, module C is the best with the larger size for longer operation time. And one of the reasons we see that with the third round evaluation, we realize that the infant quality is actually worse. So we have more contaminants, pollutants coming in from the upstream, from the catchment in the hillside in the Guntong area. So that actually, with more pollutants, the larger size would be more resilient, more forgiving, that can sustain the good performance for a longer time until in the second month until the clogging appears. So the module B smaller size, the clogging appears in the beginning of the second month, while for the larger size, the performance can be sustained for across 2 months. So these are a summary of the overall removal with the second round low turbidity scenario that we can remove 94%, and the third round that the smaller size module B slightly dropped to 93%, but still a very good removal. While for a larger size, the low turbidity 80% removal, while with the high turbidity is a 99% removal and sustained longer. So it depends on the filter design, depends on the quality of the incoming water. And we further suggest some future full-scale design with the operation, with the maintenance and the cleaning for the filter to be installed in stream, so that to enhance the quality of the water, so that people can have a better river park to appreciate the natural environment in the urban setting. So that's the use of the filter for the river quality. And then the field scale test too, which is more integrated with the soil, not just a rock and sand filter, but also the soil media. And we can apply the soil media as a lateral filter in a sense, in a setting like a rain garden or bioretention cell. Or if we have a horizontal flow with inclination, then there will be bounce well. So the rain garden is more like a vertical flow mainly, while the bounce well, we will deal with the flood risk, and we have a horizontal flow with an inclination to drain the water from the surface as well, besides the vertical percolation. And we have different guidelines in the States, UK, Singapore, Australia, and we make reference to their designs and so. And this is one of the design that I serve as an advisor for the DSD and the consultant working on the island yeast bioretention cell design. That's the engineering design that we work with the consultant together. And this plant has been installed and being test run at the moment in island yeast, which is next to the roadside. So collecting the surface runoff from both pedestrian pathway as well as the vehicle roads. So you see that's collection from both sides, so that we can do the test in the real scale evaluation. But at the same time, let me show you some other full scale tests, which we have full evaluation results. So this installation of the bounce well and the bounce well and the bow retention cell, was also known as a rain garden, which is a part of the sewage treatment works in Stonecutters Islands, and which is installed and operated by the DSD. And we serve as a project investigator and advisor to evaluate the performance. So there's a field operation with the plant and the flow path, and then the sampling point that our team work on with the rainfall, simulated rainfall. So this is a simulated rainfall so that we can have better control of the water quality and the flow rate so that we can evaluate the performance in a scientific way. So this is the rain garden, and the other drainage point that we can collect the sample as well. So these are some basic parameters with those engineering design and comparison to the guidelines in Singapore, for example, because Singapore is a tropical region, so that could be a good reference for us as well. And sometimes we realize that in Hong Kong and also maybe in other high densely populated area, that we have a very busy underground, busy network, pipelines and power lines, gas line underground. So sometimes the depth may be a limitation. So the depth of the soil filter and the drainage layer may be a limitation, like the case we have in the project here with the DSD. The depth is not ideal. So that is actually compromising the performance because the depth of the soil cannot be as much as we want, according to guideline or other lessons learned from the overseas experience, because we have too many power lines and pipelines underground. So, and also other concerns that we have to recognize is in the tropical or subtropical regions that we have a high rainfall. And like in Hong Kong, we have a very intensive rainfall in the summer times, while in the winter times, we have very little rainfall. So basically all these 2,400 millimeter per year actually very concentrated between May and September, 80%. So to deal with that intensive rainfall, our flow rates have to be a little bit quick. So the hydraulic conductivity has to be fast. But in that case, when we have the high hydraulic conductivity, some problem we may encounter is the plant establishment, or if you have even higher, then the plant may not be even able to survive in those soil filter media, and the pollutant removal performance may be not adequate. So we will evaluate the performance. And this is exactly the part where biochar can help to retain water, to retain nutrients, and help the plant growth, and also to help the pollutant removal. Well, on the other extreme, if you have a very low permeability, that is hydraulic conductivities, then we need a very large filter area, which may not be practical in an urban setting because we don't have enough space. So that could be a little bit different because like in the US, in the UK, Australia, they're mostly like temperate climates, while in Hong Kong and Singapore, maybe in Guangzhou, Shenzhen, we are more like tropical or subtropical. So these are a few tests we conducted with DSD, and then we simulated 2-year and to 10-year and 50-year return period for the flooding issues and the rainfall scenarios, and then we monitor the different water quality parameters with the bounce well as well as the rain garden, which we can see the pH are more or less stable or fluctuating within a small range. And the flood attenuation can be realized that the peak can be actually attenuated with the system, and can be flat out and can be delayed compared to the infant end, and also the pumping rate, and then the efferent end with different tests that the peak can be delayed and attenuated, and then the flow can be retained temporarily, so that to lengthen the time the surface runoff go through the system. And then the problem, the more issues is about the water quality. So with the intensive rainfall and high flow rates in Hong Kong, that and the soil depth may not be sufficient compared to the overseas guideline. Then the SS in the initial stage we may have some exceedance, and also in the later stage we may have some exceedance because maybe the capacity has been reached and that will be maybe some release of the trapped SS. Or heavy rainfall, basically with the current depth of the soil filter, we are not able to deal with the heavy rainfall scenario, like the 50-year scenario, which is too much rainfall to take on for the bounce well or the rain garden. Bounce well performs better because you also have a horizontal flow to drain the high flow rate, while rain garden is basically vertical flow. So if you have too much flow rate, there's a lot of flood and ponding on top of the rain garden, and eventually the performance are compromised. So we may need to make some amendment to prevent soil erosion and to enhance the plant roots and plant establishment, and also maybe considering construction of the transition layer to stabilize the particles. And then other than the SS, which is more like aesthetical issues, and also associated with E. coli and so, the nutrients and pollutants. So we evaluate the NMP and also the metals. So for the P, because the background level according to the surface runoff quality in Hong Kong, which is quite clean in terms of the NMP, because we don't have too much farmland. So we do not have a high background P level in our stormwater. So in that case, most of the time that would be the removal is around 40-50 only, and then we may not have a significant removal in this current setup. So we may need to have some amendment, like with the biochar, that we may tailor the production of biochar to remove phosphorus and also metal together, and also maybe your other amendment like the water treatment works residuals, like the alum sludge, which is basically aluminium or iron oxide, which can be very effective in mobilizing phosphorus. And for the metal removal, so with the rain garden, because it's only the vertical percolation and under high rainfall and high flow rate, so the performance, the removal like 70-some%, 80%, while some metals may encounter poorer removal, only 40-some% to 50%, and so. While bounce well can perform better from 80-some% to 90-some% removal, while for certain metals like copper may still have some compromised efficiency, like only 40, 50, 60, or 70% removal over a period. So there would be room for improvement in the existing SUDS infrastructure, and especially considering the limitation in the site with the climate, subtropical climate, high rainfall intensity, and also the shallow soil depth, soil filter. So that would be a room and necessity to integrate with like biochar and other amendments to enhance the performance. So coming back to biochar, for example, the review that we work together with our friends in UCLA, Sanjay, which I know him for like 10 years or more than 10 years now. So we also have a common interest in the stormwater and also biochar. So we produced a review on that a couple of years ago to illustrate our thoughts and potential of the room for the carbon biochar on the ground. So the properties of biochar, I believe that many of you may be aware, so I'm not going to explain too much on that. However, there would be a good potential that biochar to be integrated in SUDS or in LID in the US, which is usually termed as a LID, low impact development. And then we can, because biochar can remove a lot of a wide range of pollutants in the stormwater, especially, for example, the organics, which are largely effectively removed by biochar. And then we can mitigate the flooding and the water retention concerns, and also enhance the crop growth. So that would be a significant factor for enhancing the resilience of those SUDS or LID infrastructure. And in our recent review, working together with Poison House as well, and our other friends overseas, that to illustrate the concept about the performance indicators. So when we apply biochar into our soil, we know that it's been very effective. But how effective it is, we would like to highlight the importance of evaluating the performance with different aspects, including the chemical aspect, on the physical properties, and the biological aspect, which we make a critical review on the relevance and the potential of different parameters like the physical one, like water retention, which is one of those, and hydraulic conductivities and aggregate stability, which is very important as well in the SUDS and for the Biochar Amendment of the soil filter, and to enhance the crop growth, the plant growth, and also to retain the soil integrity, the aggregate infrastructure against erosion or weathering, and also against the surface runoff. So besides the chemical properties regarding the pollutant removal and the organic matter retention, so physical properties are also important. And also it's a full integration because we want to enhance the plant system and the microbial environment as well, so that the rhizosphere, well, the plant environment and the microbial diversity and the fungal diversity in the environment is also important. So these are the holistic evaluation and concern about the applications of biochar in soil that we would like to highlight that that our perspective together. So coming back to our third test, which is still ongoing with the pilot scale test, because we want to have a full control of the mass balance and also to integrate the biochar and observe it in fields in a better setting. So we also again work with the DSD of the Hong Kong government. That in Sha Tin and other sewage treatment works. In Sha Tin sewage treatment works.
Professor Zen, I'm
yes,
sorry. Professor
yes,
Zen, I'm
yes,
sorry.
I'm coming to the last couple of slides.
No, you cannot see your slide in the screen.
Oh, really?
Yeah, we got some problem.
Oh, sorry.
Could you please re-share the slide, the file?
Yeah, sure. What does it do? Sorry about that.
Thank you. Thank you.
Thanks for letting me know.
So, it's working well. Okay.
Okay. So I still have 2 more minutes, so I only have a few more slides. So I guess this is the last. This one is the review one, the health. That is this year, which I talk about, and then this is the field test, the pilot test in Sha Tin, sewage treatment works, in collaboration with DSD, and then we install the soil filter as we designed, and we implemented with the food waste compost and the yard waste biochar that we have locally in Hong Kong, produced in field scale, and then we select live species of the plants to grow on the bioswale and the rain garden at the end. So this is an amended control, and this is a biochar and biochar amended. And then with the test that we have a simulated rainfall with the surface runoff quality reported in Hong Kong, and then with the biochar and compost applications, you see the plants grow very well after a couple of months. And actually, this test has been run for like 1.5 years already. And that we are very pleased that our plants and our settings survived a strong typhoon last summer, and also the bad heavy rainstorm a couple of times last summer and also this summer as well. So it seems to be very resilient, and we do not need to do any maintenance so far. So basically, we do not do anything basically after installation. And we see that some of the tanks have a better growth, like the biochar addition and the biochar addition with compost together, so that will be even better, while to control the plant seems to show some stress, and also the water quality and the removal show the difference as well. So we are analyzing the water quality with the different metal pollutants and also different organic pollutants, including those pesticides and maybe emerging contaminants as well. So we are evaluating the performance, and also we are looking at the DOM, dissolved organic matter as well. So I hope that next couple of months we will be able to present you the latest finding from our well control pilot test with the bioswale as well as the rain garden. So last slide, take home the messages. Actually, these take-home messages are based on our previous lab scale studies, which we have conducted before these 3 field scale and pilot scale studies. From those lab scale studies, that we are confident that the yard waste biochar and also food waste compost will be a good amendment. And then the metal breakthrough and the flow conditions will be concerned, and the filter properties is very important. And then the components in the surface runoff the stormwater, like the inorganic colloids or the dissolved organic matter, would play different roles and have different effects, which we have to pay attention to. And the design of the biochar, how do we engineer the production of the biochar is important to tailor with the different pollutants and different performance we would like to have in the soil system. So this is a good integration, good potential for integration of biochar and also soil chemistry and soil physics for the engineering works to improve the environment in the urban settings. With that, thanks very much for your time and your attendance. And again, I'm very thankful for the opportunities from the organizers and kind chair by Professor Du. Thank you.
Thank you, Professor Zen. Thank you very much for your wonderful lecture.